So,
all right, ladies and gentlemen, let's get started. We don't want to wait for too long for the people who sleep too late. So today is going to be the first lecture by Professor Fradkin, and he's going to pretty much pick up where I left off, and he's going to tell you more wild and wonderful things.
okay. So the plan more or less is the following. Actually, there's a slight change relative to my plan. I will overlap a little bit with Ganpathy's last lecture to actually make a smooth transition. Okay. And partly to set some of my language so that we don't get confused. At least I don't get confused. All right, so the aim of these lectures is to eventually talk about the non-Abelian states, and this will be probably in my second lecture. Today we'll mostly talk about abelian states, multi-component states, and how to understand them from the point of view of topological field theory. And so I'll first give you a lightning review. Remember, just to remind you, we're talking about systems which have a fractional quantum Hall effect. So you have a two-dimensional electron gas that lives on some kind of surface, could be a heterostructure in gallium arsenide, it could be graphene, it could be bilayer graphene, or twist and shout bilayer graphene. I mean, all of these variants that people do nowadays, okay? So we have a magnetic field pointing in some direction. I'm not going to be as picky as our chairman is. There will be some magnetic field, there will be a current, and there will be a voltage here, the so-called Hall voltage. And then you're going to have, what you see in experiment, is that the Hall conductivity is precisely defined in terms of some fractions. Sometimes I will use units, nu over 2 e squared over 2 pi h bar. And if I use civilized units, yes? Yes, okay. You cannot hear me? Okay, I thought that the microphone does the job. Okay. So in those units, sometimes we write this as nu over 2 pi, depending who you are. And nu essentially is just a ratio of 2 integers, and m is odd because these things are fermions. I'm going to mention later what happens for boson. Okay. Right, so this is a dissipationless state. So originally people got confused. They thought this was some kind of superfluid because of that. So it's dissipationless simply because the system is well protected by the large magnetic field. There is an enormous gap, and you're at very low temperature, so all the phonons are dead at that point, at those temperatures. So there are no dissipative channels in this problem. And on the other hand, the current is actually perpendicular to the electric field. There is no work done for that. So this is the reason. So in some sense, you can think of this as a fluid. It's an incompressible fluid. You can also call it an insulator with some, if you're a bit liberal, in the sense that it doesn't have any low energy local excitations, much like an insulator does. So it's a mixture in some sense. In some sense, it's a liquid, because if you try to apply, say, a shear distortion, it will not actually, there will be no work done, like in any liquid. Okay, so if you try to distort the system with, say, a shear distortion, there will be no energy cost for that. In that sense, it's not so it's certainly not a solid. Okay, so it's a liquid state, but we can sometimes refer to it as if it were essentially an insulator, except that it has these marvelous edge states that people talked about, aside from other things. So for the simple states, nu equals 1 over m, we saw, and Ganpathy gave a beautiful introduction to these so-called Laughlin states. And the Laughlin states, so first of all, one works typically in complex coordinates. So x1 and x2 are x and y. And the Laughlin states, all of the particles have coordinates zj, and the Laughlin states up to some normalization, I and j is zi minus zj to the power m times an exponential factor where L naught squared is 1 over h bar c over EB, and in my units is 1 over b. So there are two ways to think about it. Actually, Ganpathy wanted to think that the limit of interest for this is a limit where you artificially set the inertial mass to 0, which is one way to think about it. But the other, which says you send the magnetic field to infinity, which means that the length scale of the problem, which is the magnetic length, goes to 0. And so you're not going to explore what happens within a magnetic length. By the way, yes. By the way, I have to warn you about two things. My native language is Spanish, and we have 5 vowels. English has about 26. And I will do my best to help you make the mapping to my 5 universality classes. So sometimes this leads to interesting confusion. So I would say, for instance, in class, this week we're going to use Wick's theorem to study weak interactions. And I pronounce them exactly in the same way because I don't know any other way to do it, much as I try, okay? Okay, so that's one. The other is I tend to mumble. My mother complained about this, and with working a different language accentuates the problem.
I will channel your mother.
So actually, there was a movie made by students in Urbana at one point, and my character was like it's called I forgot the something park, whatever, South Park type movie. My character had a beard, and when he spoke, the beard moved up and down, and they put subtitles. So during COVID, in fact, I gave lectures, online, or if you want, by Zoom. So he said, no problem, we're going to, Zoom has, subtitles. They were total garbage. Nobody could understand anything. So they have to hire students to actually translate the translation. All right, sorry. Okay, so bear with me. There will be some interesting confusions because of it. Okay, so I prefer to think of this problem as the limit where the magnetic length is small. I know that at least at the level of the free particle problem, you can think about either way. For instance, for the gaps, it's the same. You can send B to infinity or the mass to 0. But if you want to think in terms of the correlations of in what length scales you want to write down your theories, then it's important to know that the length scale is very small. And we are not going to investigate the physics inside the magnetic length. Is this clear? Okay. Okay, so the Laughlin states are very simple. Then there are the generalizations of them by Jane that Ganpathy covered marvelously. And the Jane states come in 2 types. So there are 2 indices, P, let me call them P and S. There are 2 series, in fact, for each case here. P over 2 is P plus or minus 1. In Ganpathy's lectures, he chose this to be a plus sign. So that's usually the normal Jane sequence. There is also a so-called reverse Jane sequence with a minus sign for the particular case where S is 1, which is the sequence for 1/3, 2/5, 3/7, etc. the reverse sequence is 1, 2/3, 3/5. You get it, okay? And they have somewhat different properties. Because at the Landau level, if you send the magnetic field to infinity, you cannot excite particles to the higher Landau levels. So in this particular case, if you're in the middle of the Landau level, in fact, this is precisely what Ganpathy did when he talked about the so-called HLR theory of Harper, Lee, and Reed. Sometimes I get confused with LHR, which is actually a code for London. So when I was looking about my codes, I was thinking of HLR, but it was LHR. Okay. So in this case, they converge to 1/2 from both sides, from the particle side or the whole side. But this is a property of all of them. So as P goes to infinity, this goes to 1/2s, and they can also converge for both sides, even though in the other cases, there is no particle-Hall symmetry. There is a mirror symmetry of the James states. Actually, if I have time in the last lecture, I will mention something important about this, and which is actually of current interest. Okay, so this is a lightning review of this part, just we understand each other. Okay, so these particles, so this interesting state, in addition to have these precisely defined values of the Hall conductivity, it's a little tricky. In 2 dimensions, conductivity and conductance are the same because they are dimensionless, but they are measured differently. One is a local measurement, the other is a non-local measurement. So for instance, in the picture there, what you do is you measure, as Ganpathy explained, the voltage here, you use that voltage to define the electric field in a sense. And then you look at how much current goes through, and from there you can extract the whole conductance. But you can also measure that with local contacts. Okay, and that will give you the conductivity. They are not the same, by the way. At least in the Hall effect, when you're in the fractional regime where there's a gap, in fact, you can relate one on the other. In the compressible regime, they are different. And you have to be careful with that. So the excitations, as we saw, are in some generic sense vortices. Okay. I'm told that there's a dense fog advisory in Chicago for some reason. Okay, so they carry fractional charge. And for this, all of these states is just the denominator of the filling fraction. It's just that. And they carry fractional, called braiding statistics. In the sense that if you start with some state, some initial state, and you think of this as time, and this is space. So you have a vortex located at A, another vortex located at B, and they evolve. You can go into a state where A ends up here and B ends up there. So we call that an exchange process. Okay. Notice it's not done at the level, in this sense, it's not done at the level of the actual wave function, which you can always also do. This is understood in the sense of an exchange process. Okay. So, but notice that I draw this, I'm going to call things world lines, which is essentially a curve in space-time that these excitations actually trace in their evolution. And you can define, in a sense, a wave function for the initial state and a wave function for the final state. And then what you get is that the wave function phase, and that phase actually has a plus or minus depending on how you actually braid, which is pi divided by 2st plus minus 1. Again, it's a denominator. So these things are called anyons. Okay. So it's a new type of statistics that is allowed because you're in 2 dimensions. You can define some version of this in 1 dimension, but it's somewhat arbitrary in a sense because in 1 dimension, in fact, these anyons, notice that these word lines do not cross. I don't allow them to cross. Otherwise, the sense of braiding, the notion of braiding doesn't make any sense because I can have particles colliding each other and then they will cross. So there will be nothing particularly stable about this. So there is no such thing as a free anyon, in spite of many claims in the literature. Anyons have, you may call it a quote, hardcore, because they cannot go, you cannot put 2 anyons in the same place. Otherwise, the notion of fractional statistics is ill-defined. In 1 dimension, on the other hand, if you do the same, if you order particles from left to right, in principle, there is nothing in the dynamics that will change that ordering if they have, essentially, if they have a hardcore, or even if they are Hermions. Okay? So you can actually do it eventually, but in 1 dimension, to some extent, the notion of statistics is somewhat arbitrary. Now, it turns out there is an additional.
Let's do
Yeah, but no, if you have a large number of particles and you want to do it for some collection of particles, then it doesn't depend on the boundary condition. If you have 2 of them, yes, you can go around coming from the other side. For all of them, but if you need to do that for pairs in various.
Not pairwise.
Yes. No, but for pairwise, you cannot do it in general. Yes. So in principle, as I said, in 1 dimension, we can argue about this, but it depends on one's definition. Okay, so we can have other things like parafermions, for instance, which I unfortunately invented the name back in 1980 with Leo Kadanoff, because we don't know how to call them. And it's a bad name because there was something called parastatistics before to explain why you can have 3 quarks in a nucleon without, just without spin, just with spin, because they don't know the notion of color at the time. It turns out that the notion of parastatistics is actually inconsistent with the axioms of local quantum field theory, and so it's not allowed. So in that sense, the term parafermion, which evokes that name, is not a good one, but it's stuck, so I have to live with my mistake. Yes. Yes. Yeah. They are the same. They were about the same time. Greenberg, and there were various people that were doing that. The motivation actually was because in nuclear physics you have, so in the nucleus, if you accept what at the time was called the quark model, then there seemed to be an inconsistency. So they wanted to relax the notion of occupancy. In a sense, the notion, Haldane's notion of exclusion statistics is somewhat related with that. And for that reason, even though Haldane says that works in any dimension, it has only found the home in a number of integrable systems in 1 dimension, as far as I know. Okay. So whether actually these guys actually are versions of exclusion statistics is a matter to be settled. Okay. Right, so much for history. Okay, so this is what one has. Okay. So notice that I introduce a notion of braiding, and braids actually form a group. And in fact, the notion, this subject actually has a long history in different areas. The notion of the braid group actually came from the solution of the so-called the solution of the 6-vertex model in statistical mechanics. And there is actually temporally and Liv realized that that in that system, for certain values of the parameter associated with the 6-vertex model, there are these excitations that have interesting properties, and that's where they formulated the rules for the braid group. So they are related to, is inherently related to topology, but this was done in some sense with 2-dimensional statistical mechanics or 1-dimensional quantum mechanics, depending how you think. Okay. Now, I'm going to give you now a hydrodynamic derivation. So what I want to do now is to rephrase some things that was done by Ganpathy. I never know how many Y's I'm supposed to. Okay. What I want to do is to construct a minimal theory for this problem based on very few assumptions, and there will be no microscopic considerations in what I'm going to say except for one, but I'm not going to do a microscopic derivation. So it's a heuristic argument. As a side, I want to remind you of a famous, I don't know how many of you read Landau-Lifshitz, the classical mechanics book? Okay. Okay, we all did, right? In kindergarten. I went to a good kindergarten. Okay, I did, okay. So they have a quote derivation of the Lagrangian of a free particle. It's not a derivation, it's a symmetry argument, much like the one I'm going to use here. So the argument in the case of Landau-Lifshitz so much for the people that want to be way past Landau, okay? Okay, so they say, well, we have a free particle. They have location R that may depend in time and some velocity that may depend in time. And I want to know what the Lagrangian for the free particle is. In principle, the Lagrangian will depend on both R and the velocity, which is the time derivative. Now, if the particle is in free space, it cannot depend on the position because free space is homogeneous. It's translational invariant. Okay, so translation invariance requires that the Lagrangian be only a function of the velocity. On the other hand, free space is isotropic, doesn't have a preferred direction. So it depends only on the absolute value. And now this is a key, an additional assumption that one makes. You want the equations of motion that result from this by doing the least action principle to lead to local equations. In other words, to local differential equations. And therefore, this has to be an analytic function of the velocity, but the absolute value, as you know, is not analytic because the absolute value is a square root of Vx squared plus Vy squared plus ABZ squared. And there is a square root here that's not an analytic function. So this has to be a function of V squared only. Okay, now we need to make assumptions. So that's all you can, so now I use the homogeneity of space, which is translation invariance, isotropy, and actually this is what I will call locality. The assumption that this is only a function of V squared. Otherwise, the equations of motion will not be local. Okay, so you don't want to have action at the distance, although Newton did have action at the distance sometimes. Okay, so that's what this is. And then you say, okay, if V is small, then L of V squared is some constant. That's another constant. That's V squared. And we call this other constant the mass divided by 2. Okay. Turn it on. Yes. 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 Maybe it hasn't. Yes.
So in general,
Pick up, please. Yes.
yeah. So if we add a total time derivative term to any Lagrangian,
I cannot hear you.
so if we add a total time derivative term to any classical
Yeah, but this
Lagrangian,
will have no effect on the equations of motion.
yes, that is the point. But how are we writing the Lagrangian here based on those symmetries then? Because it's the equations of motion.
If it is actually, yeah, the equations of motion, then you write down the action and you do the variation of the least action principle. I'm not going to go through that and you derive Newton's equations, okay?
Yeah.
Okay. In fact, this provides for a definition of what the force is, whereas the second law is actually tautological, as we all know, because there is no definition, independent definition of the force. Okay, this provides a definition of the force with some assumption.
Okay.
Okay, but that's not the point. So there are these constants that, in principle, you get from experiment what they should be. Okay, so this is sort of in the philosophy of what I will call, or people call, an effective theory. So this is what the Lagrangian at slow velocities has to look like if you make all of these assumptions. And we don't question this when we in kindergarten learned about this. Okay. Now this is not the only solution. There are other solutions. For instance, I can write the following other solution, that the Lagrangian is mc squared square root of v squared over c squared. And this is the Lagrangian of a free relativistic particle. Okay. There is an additional assumption here which has to do with Lorentz invariance, which I didn't make here. So if you impose certain symmetries and assumptions about locality, then you can actually get a great deal of mileage. A lot of physics is done that way. Nobody derived this. I don't call this a derivation. Once a mathematician wants to ask me if I can prove this. But you cannot prove this. Okay, this is just the way we work. Okay? I'm going to use the same philosophy for this problem. So what do we know about these fluids? We know there is a magnetic field. And B is not the same. So B is out of the plane, but B and negative B are different. So there is a broken time reversal symmetry. And in fact, there is also a broken parity symmetry on the plane. And here parity means a mirror symmetry. It's a reflection across a line, essentially. So if you make both transformations, then you get essentially the system is invariant, but not if you make only one of them. The other condition is that the system is incompressible. That means that all local excitations gap, which I will take to go to infinity and make it as large as possible. I'm interested in what happens below the gap. Okay? So I'm interested in the long time regime, the low energy regime, defined in this way. It's a charged fluid. And that means that there will be a 3 current, and this will be the charge density, and this is the usual current, and it has to satisfy the continuity equation as in Ganpathy. Okay. I'm going to show you that making these 3 assumptions and constructed the only possible theory at low energies, which he also sketched, you basically get the so-called hydrodynamic theory of the quantum Hall effect, essentially with no more assumptions than this. Okay. So this is an argument that was first made, as far as I can recall, by Fradkin and Z. Fradkin usually complains that I don't cite him. He never cites me, on the other hand. And when I cite this work, he says, oh, you cited because it's with Z who lives in the US. So there's no way to win with Fradkin. So the argument goes more or less as follows. If the current is conserved, it has to be the curl, at least locally, it has to be the curl of somebody else, of some vector field, which I would call little a because it has nothing to do with electrodynamics, up to some coefficient that will choose for convenience to be 1/2 pi, but you can negotiate. So clearly, because this is a curl of a vector field, and this is satisfied, notice that this field A, if I make transformations, some smooth function. Yes. By the way, much of what I'm going to do will be done in real time in the Minkowski signature. I will not use imaginary time unless I need it. So remember that the Lagrangian is T minus V. In the Euclidean signature looks like T plus V. So they are funny signs that you have to be careful. Okay, so if you make this transformation and phi is smooth, so it's not the so-called singular gauge transformation that we heard about, then the current does not change. So this looks like a gauge transformation. Now I want to write down an action. People say physics is where the action is, right? Okay, I want to write an action not for J, but for A. So it's going to be the integral of some Lagrangian. Okay, so it's a Lagrangian that will depend on A mu and on the derivatives of A mu. I just told you because of this, it has to be gauge invariant. That's one condition. Many of you saw me probably dozing off during the talks. I tend to fall asleep in seminars. I feel embarrassed. I wake up and I force myself to ask a question. It's a theory talk. I usually ask, is this gauge invariant? And about more than half of the times, the speaker begins to make excuses for why that is not important, which means it wasn't. It's remarkable how it works.
Yeah, you actually fell asleep at one of my talks.
I usually fall asleep. All right. So I'm going to make, so it has to be gauge invariant. Okay, so you could say, well, you can write something like, let me call little f mu nu, as Ganpathy did. Okay, but who said there is a local function of f mu nu? Okay, or some other object. Now, the incompressibility means that this can be a local function. Okay, so I'm going to write L as some local function. So this actually is what implies locality. But this tells me that it has to be odd under time reversal. And the Maxwell term that you will normally write, let me write it here for you. By the way, if you look at these gauge fields of this type, any gauge field, have units of inverse length. If you set H bar and C to 1 and all of that. I like this choice. I don't put the usual, when I write my covariant derivatives, I don't put the electric charge there because it changes the units. Okay, so I prefer to do this, is more geometric. So this guy here has units of 1/length to the 4th, first of all. That means it has a coefficient here, some coefficient, which is effectively some number divided by the gap, if you actually put the units together.
Hi, I have a question.
Let me finish and then I'll come to you. To that. So this term is perfectly local. It's time reversal invariant, not doesn't break time reversal, like Maxwell theory. But because of the units, this has to have a length energy scale here, if you want, which is the gap. So if the limit where the gap goes to infinity is what I'm interested in, this term should be unimportant. So A, it has a wrong symmetry. It's perfectly symmetric. It's there. There's nothing wrong with it, but it's not the leading term. So in order to remember that you want an action, and the action, the volume has units of length cubed. So that means the Lagrangian density has to have units of inverse volume, which is that, just by dimensional analysis. And this has units of length to the fourth. So that's inverse length to the fourth. That's why I have this consideration. Sorry, you had a question.
Yeah, why it has to be that f square? That is because of locality.
I didn't use a square. Where is a square?
F square.
Oh, this is the Maxwell Lagrangian. In electrodynamics, if you write the Lagrangian for Maxwell, it's usually in the textbooks, it's written as 1/2 e square minus b square in 3+1 dimensions, right?
Yeah.
But if you actually work this out, what it is a fourth of f mu nu squared.
Right.
Okay.
So I was actually thinking that you were writing the Lagrangian
Yes.
the way you actually, I mean, demonstrated for the classical mechanics.
Sorry?
For the classical mechanics, the
Yes, it's
free
a
particle
Lagrangian. It's a
Lagrangian.
Lagrangian.
Yeah.
Remember that this is a theory, is a field now, because the current is a field.
Yeah.
And so it's a Lagrangian density that you will have.
Right. So
that's why I write it this form. Remember, d3x is dt d2x, right? That's what that means.
right, that is. Yeah. So then, I mean,
This is the Lagrangian density.
it's a Lagrangian density, right?
Yes.
So there you have, I mean, added in the Lagrangian that you have, I mean, argued that the Lagrangian is a function of the v squared because of some locality.
Yes, I'm going to come to that.
Okay, okay.
Okay, this is local. There's no problem with this. This is perfectly local.
Okay, so
There's nothing non-local about it.
okay, can you remind me once more that why it has to be squared to be a local?
Because otherwise the equations of motion will not be local, will not be local partial differential equation, will be non-local equations. So for instance, if you have an operator like the Laplacian, and you compute the square root of this is an ill-defined object, it's a non-local object.
Okay.
Okay?
Now I understood.
Okay. So you want locality. Okay? This is why this notion of doing the gradient expansion is meaningful. You get local expressions. Okay. Okay, so the question is, we want a term that actually is gauge invariant, is local, but is odd under time reversal. And this term is precisely this Chern-Simons term that we heard about. Let me erase it for a moment. And we're going to write it as some number divided by 4 pi. A lambda. Okay. I'm going to drop the Maxwell term. This term, as you can see, is first order in derivatives. And this is the epsilon tensor in 3 dimensions. So that means that in particular, if nu is 0, which is time, so mu and lambda have to be space, I and j. So in particular, it has one expression like this. Okay, so this, and notice that A has units of inverse length, and there's another unit of inverse length here. So this has units of inverse length cubed, or inverse length cubed. So this cancels the units of the that you have here. That means that this is a dimensionless number. Okay. Now, for reasons that Ganpathy explained beautifully, if you actually put this in something we're called a closed manifold, and then you can do finite temperature, or even at zero temperature, if you simply assume that the manifold is closed, then the large gauge transformations, which are not these ones, these are the local, the small ones, and come to those in a moment. The large gauge transformations require that this has to be an integer. So M has to be an integer. It doesn't say that this integer is even or odd, could be positive or negative, okay, but it has to be an integer. Now, how do I couple this? Yes. Let me finish the argument, then you ask me the silly question. Okay, so the original object that I had was a current. If I want to couple this problem to an external electromagnetic field, an honest-to-God electromagnetic field, I need to write a term that will look like J mu, a mu with some electric charge here sitting. Okay. But what is J? J is this. So that means that the term that couples this problem to electromagnetism will look like this. Times A mu. Okay. So this is just J dot A, good old J dot A. And you can do that because this is a gauge theory, it's a gauge field, so it has to couple to a conserved current, otherwise inconsistent. Okay, so there you go. In principle, I can have an additional term that couples some set of currents, let me call them quasi-particle currents for now, that couple to this guy. And this actually will turn out to be, the J is essentially, is a simple local way of writing a distribution of word lines of this quasi-particle. You can write it as a sum of delta functions, etc. Okay, so this is it. Okay, so notice that these assumptions essentially tell you that in the low energy limit, it cannot be anything but this. Now you can have more terms, as we discussed before, or he actually discussed. You can have the Maxwell term. Those terms have scales in it. Okay, all of them will have scales. So this is sort of the universal low energy action. To write this for a generic quantum Hall system is complicated. For the abelian states, I'll show you how to do it. This is a so-called K-matrix theory, which I will go shortly.
Hi,
Okay?
can I ask
Yes.
a question?
Somebody had a question before, and you had a silly question.
I have a silly question.
Yes.
So is there any reason you always relate locality to incompressibility?
Yes,
But I mean, it's not if and only if.
yes, it is.
Why?
Because locality,
Why it's if and only if?
because the gap is essentially, you have, first of all, the length scale is a magnetic length, which is very short. So I'm going to look at things at length scales, which are long compared to the magnetic length, number one. Number two, incompressibility tells me that there is an energy scale to all excitations. So I want to work at energies which are low compared to those. And in that limit, you get locality.
I understand that argument. That argument is in one direction. There is no local electrodynamics. That is also, I mean,
this is not a, this is a vigorous. No, this is a symmetry argument, Gerardo. This is just.
No. I understand in one direction.
Yeah.
I'm not arguing in one direction.
I don't know if you find an exception to this, I'll be happy to know it.
Okay.
As far as I know, it goes both ways.
Okay. Okay.
Somebody else had another question.
I had a question on the result. Yes. So you dropped the F² term because of dimensional consideration.
Well, not only that, it's simply because it has more derivatives. So it has, so if I calculate any observable with this theory, it's like some correlation function, in the long distance, low energy limit, these are the only terms that will matter. If I include the F² term, they will affect at shorter distances. And then you will begin into the question, are you on the scale close to the magnetic length or not?
Yes, but like we initially assumed that the dimension of A is 1/L. But I could have gone the other way, right? I first write down the terms that is in the action, and
Okay.
then
Fine. In the way it's usually done in the textbooks for electrodynamics, they have something like this, right? And so either you have it here or you don't. When they don't, they normally have it in the covariant derivative.
yes,
And then that means that the vector, because they're in 4 dimensions, it doesn't matter because the fine structure constant is dimensionless.
Yes.
But if you go to 2 dimensions, 2 + 1 dimensions, as here, the fine structure constant will have units. And
yes,
that will change the units of the vector potential. And I don't want to do that. I want to define my vector potential. It's actually what mathematically is called a connection. So that's why I want to have it units of inverse length. It's a choice that I make.
I see. Okay.
Okay, let me continue.
Yeah, just a minor point. So regarding the F² term, so the idea is that you want it to be F² because of constructing Lorentz invariant scalars, right? But F by itself is it comes from locality. But the F² is because of you want to construct Lorentz invariant scalars.
Not only that, it's the fact that it depends on the squares, like the velocity square. I cannot write the absolute value of F. Okay, I could have written the absolute value of F, which is a non-local object.
Okay, I see.
So I have a question. So following this question only. So
Yes.
this, when you wrote the initial action, that has nothing to do with the Lorentz invariance, or it had?
This theory has, actually it's Lorentz invariant, but it's actually more than Lorentz invariant. That's what I wanted to say next.
I see. Okay.
Okay, so let me look at the action of this theory. So let me write it in shorthand. From now on, it will be M over 4 pi A dA, as we learned from the boss. A dA, boundary terms, minus J quasi-particle. Well, if you want, I can put some indices here for just to be general. Okay? I'm going to use this index-free notation. But as he explained, this is the same as that. Now, look at this action, not the Lagrangian, the action. And is M over 4 pi A dA. Let me ignore everything else, just keep that. Suppose that I actually make a coordinate transformation. Instead of working in encode-free space-time, I work in a more general space-time that can be curved, wrinkled, warped, whatever you want, okay? It will have some metric in that case. And I use here, for simplicity, the Minkowski metric, which is this, but you could write it for any metric. It turns out that this Lagrangian classically doesn't depend on the metric. So in particular, it means that the variation of the action as you vary the metric is 0. So in fact, it has a huge symmetry. It's not only Lorentz invariant, it's invariant under general coordinate transformations, so the most general that you want, provided they are smooth. Okay, it has an enormous symmetry. For this reason, we say that this is a topological theory. This is one of the reasons for why this theory is topological. It has no content that is associated with a metric. And this is why, in the end of the day, all of the observables that you can calculate depend on things like the linking numbers and things of that sort. They don't depend on distance. They depend only on topology. This is true classically. Quantum mechanically, there is a slight caveat. There is an anomaly called the framing anomaly, which I will not discuss. But there is a slight caveat, and this relation is related to the existence of what is called the topological spin for this excitation, and the consistency with the spin statistics here. But that's a technical issue, and I will read Witten's paper. You can read Witten's paper in 1989, where this is there. Okay, so what I want to do next is to take this theory, and I want to quantize it. Think of this as some dynamical problem. I'm going to use the axioms of quantum mechanics, or quantum field theory in this case, to write down a quantum theory of this. And I want to know what is the quantum theory that results. Then we're going to apply this to the quantum Hall effect. Okay? Okay, so let me now write the so-called Chern-Simons Lagrangian. M phi. Well, let me write the epsilon tensor now because I will need it. And let me write the coupling of some current. In that case, it's like this quasi-particle current, but let me just have that. This current has to be conserved, which is before. This is now the quasi-particle current, now the electrical current is this other option. So let me actually do something you never do, which is to expand this in Cartesian coordinates. Okay? There was a question the other day about the role of A naught. And this you will see here. So the Lagrangian in Cartesian coordinates can be written as A naught times M after some reshuffling of things over 2 pi epsilon ij vi kj minus A naught plus M over 4 pi epsilon j ai d naught. Doesn't matter for the time, doesn't matter where you put it. J plus J. Sorry? Lowercase. Oh, yes, sorry. Of course, you saw that. Okay, so if you stare at this and you went back to your theory of constraint, even classical theory of constraint systems, you recognize that this guy is a Lagrange multiplier. By the way, if you do the same calculation in electrodynamics, you will get the same thing. So for Maxwell, E and M, you will get a term that will look like A naught times the divergence of the electric field minus the charge density plus other terms. Okay, so when you write it. For this reason, in this case, you get Gauss law. So this is a constraint that enforces the condition that this is equal to the charge density. The Gauss law is a constraint, and in fact, in the quantum theory, is what one calls a generator of time-independent gauge transformation. Okay. I'm going to come to the quantization now, but I need to start, in the beginning there is a Lagrangian. That's where things begin. I'm doing this now. Okay, so the analog of this here, if you read that, it says that the charge density, it's a function of time if you want, is m over 2 pi times the curl of little a. Let me call that little b. So b is the curl of a. And so this theory tells you that if I have a charge, or if I have a particle, then it carries this flux. So Chern-Simons is a theory of flux attachment. Okay, it's automatic. Okay, this is in fact the Gauss law for this theory, and it plays the same role as this does in electrodynamics. There's no difference. Okay, of course it looks different because the theory is different, but it's the same, plays exactly the same role. Okay, so this is one condition. So this essentially is a constraint that gives you this Gauss law, which means flux attachment for us. It's also the generator of time-independent gauge transformation. So this is, okay. And the reason this happens is because here, as in electrodynamics, A naught doesn't have, there are no terms in the Lagrangian that depend on the time derivative of A naught. So it's not a genuine dynamical field. It's a constraint field. It's a Lagrange multiplier. That's the correct way to think about it. So sometimes people go to a gauge where A naught is 0, and then they force this as a condition in the space of states, which is the Gauss law. Okay, we do the same here. Okay, now I want to do something else.
Hello.
Just a second, let me continue, then I'll answer questions. Okay, so now I stare at the other terms that I have. The other terms, if I look at the equations of motion, which you obtain by differentiating this relative to the vector potential as usual, they tell me that this is m over 4 pi epsilon u lambda little f lambda. Remember that this is the f for these little guys, and this has to be equal to j mu, this j. So this is the analog in electrodynamics. You write this, right? It's analogous to that. Okay. Now I want to quantize this theory. So far everything is classical. So how do I quantize it? So you look here, so you have to, so in my kindergarten also they told me that if you write the Lagrangian as p q dot minus h, if you want, is the Lagrangian in that case, then you identify this to be the canonical pairs, with p being the canonical momentum and q being the coordinate. So I want to do that here. But notice the following. Well, I can do an integration by parts and write this as A1 and A2, and then there's a factor of 2 and not 4 in that case, because we get rid of the antisymmetry. But it tells you that A1 is the conjugate, that the conjugate of A1 is the time derivative of A2. The time derivative of A2 plays the role of the canonical momentum for A1. That means that A1 and A2 do not commute in the quantum theory. In quantum mechanics, these things are promoted to operators, say at equal times now. So with my hats, I will drop my hats later, no pun intended. And if you look at the coefficients, you find that this is I times 2 pi over m times the delta function of x. Okay. So you ask, what is the Hamiltonian? The Hamiltonian is just J dot A. That's all there is to it. If there are no currents, then there is no energy, which is what I told you before. There was no energy in this problem because it was this huge symmetry. Okay, so the Hamiltonian is just that. And of course, since A1 and A2 do not commute, this is non-trivial. Okay, so it has some dynamics because of that. All right, so this is actually behind much of what we're going to do. So there are two ingredients: flux attachment, which is essentially the Gauss law. And this, it means I have to take my physical states have to be such that this identity is always satisfied, so that J naught of x minus m over 2 pi times the curl of A, which I will write now as B of x, annihilate that. Okay, so that means that the Hilbert space is a gauge invariant Hilbert space, because this object is the generator of time-independent gauge transformation. So gauge invariance, okay. Now there's a question of the quantization of M, and there's one way to do it with this monopole argument that we heard. That is, I'm going to do it somewhat differently because it will illustrate why we have an n-fold degeneracy on the torus. Okay? But it follows essentially much from knowing what the equations of motion are and what the commutation relations. There is nothing more than that. Somebody had a question.
I had a question, yes.
Yes.
So just to get back to your analogy between these three-dimensional and two-dimensional gauge theories.
Yeah.
So as you said in 4 and 3 dimension. In 4 dimension, what Gauss' law we got from the Lagrange multiplier is equivalent to the flux attachment. But also
No. It's not a question of dimensionality. If you do electrodynamics in 2 + 1 dimensions, the conjugate variable of the vector potential is the electric field in any dimension. This has nothing to do with dimensionality. This is the question of broken time reversal. And so the theory has to be topological. Maxwell is never topological.
yes.
So it's a special property of this theory. But it's a gauge theory, like all gauge theories have a Gauss law. Okay? And
Yes.
what I told you in this case, the Gauss law is flux attachment.
I see. I see. But in general, when we think about Maxwell's theory, then we also think about that the Gauss law allows us to count the number of monopoles that are present in a theory, right?
There are no monopoles in electrodynamics.
Yes, not
you
magnetic.
You count charges because you get divergence. The Gauss law is divergence of E equals the density.
Yes,
Okay,
so
this is
I
the
wanted to make
analog of
charge.
this. That's the analog of this expression.
I see.
So the analog of divergence of E is just B.
I see.
I have a question. So the Gauss law in that was the Gauss law in 2 dimension, which you finally effectively wrote down.
Sorry?
It's a Gauss law in 2 dimensions.
It's not a question of dimensionality. It's a Gauss law for Chern-Simon's theory.
Okay.
If you do electrodynamics in 2 + 1 dimensions and 3 + 1, the Gauss law will still be divergence of E equals
Yes,
rho
I agree, but it has
in
implications.
any dimension.
I completely agree with you, but the implications for the potential, form of the potential
Oh
will
yeah,
change.
there will be, instead of being 1 over A is logarithmic. I know
Yes,
that,
this
but
will
yeah.
be log. So
Yeah,
what
but
does
here
it
there is
mean?
none because there is no energy.
Okay. Because there is no energy, this has
Because
no
the thing is
consequence.
topological, then you don't have the Coulomb, there is no Coulomb potential or anything like that. There's no
I see.
analog of Coulomb, of the Coulomb law.
I see. Okay.
In fact, the analog of the Coulomb law comes with units, right? Because the fine structure constant has units in 2 space dimensions.
This logarithm is of no consequence in that sense.
No, it's not. In fact, if I have this f mu nu square instead, there will be a logarithmic interaction. But this term actually is more important. So originally, by the way, Chern-Simons was discovered, of course, by Chern and Simons. But in the context of field theory, it was discovered by Desser, Jacquif, and Templeton, I think, back in 1982. And they wanted to have the f mu nu square term, so they thought of the mass of the Chern-Simons term as a mass term, because it gave them units of scales. Okay? But if you take the limit where the mass essentially went to infinity, all that remained was this. So the topological character was not appreciated at the time. Not until Witten's work in 1989. So that's a historical note.
You again explain why that statement of current written in that form is a statement of flux attachment.
Because it tells me that if I have a charge, I have a flux. It tells me locally, if at point X I have a charge, at that point I have a flux. That's what B is. It's a curl of A.
Right, not
Well,
del.
call that the flux. If you want to do an integral over some small region, then it will be the flux. It will be the charge in that region will be given by the flux. So we call this, maybe with an abuse of language, the flux attachment. It's a local flux attachment. Okay, so notice that the Hamiltonian is just this. So if I don't have currents, the Hamiltonian is 0, which is telling us already that the theory is topological. Okay, let me do something a little better and discuss now the relation with the edge. from just this perspective. Okay, I'm going to set from now on 0, so I'm going to set the current 0. Then we'll work in vacuum, so to speak. And this will be time. Here I'm going to have space. I'm going to think of my cylinder, my space-time, so to speak, as a field cylinder. We call this the M will be this manifold, this field cylinder. It's going to have a boundary, which I'm going to call sigma. Notice that this is time and this is space. The time slice is going to be a disk, D. And the vertical direction, essentially, is just time, which is R. If you put that in periodic boundary conditions, we can negotiate later, okay? So, but the boundary of the disk is a circle. Okay, so that's the contour. So the manifold M, the field cylinder, is the disk times time. The disk that I sweeping time. Okay, that's all there is to it. And suppose I now take, and this is something that I'm not going to repeat in detail what Ganpathy did. This theory has problems at boundaries. It's not gauge invariant at boundaries. So if you make a small gauge transformation, we call that I. Then the change in the action is the integral over that. So do some calculations, you find that is equal because this capital phi times a quantity that I will call F mu star. F mu star is the dual of F mu nu, is 1/2, then mu lambda F mu tau. So the dual of a second rank tensor is first is a vector. Okay, but this integrates to the boundary because it's a total derivative, as you can see. And what is the boundary is circle times time. Ds mu, so it's a surface integral of phi times. It's just that. So this, I can call this sigma. This is what I was calling sigma. So it's the circle, which is the boundary of the disk, sweeping time, is what is called sigma there. Okay. Now, the equation of motion, in this case, says that F mu nu is 0, because I don't have currents. That means that F mu nu, up to large gauge transformations, is just, sorry, that the vector potential is a gauge transformation, up to large gauge transformations that we'll discuss in a moment. So if you plug this into the action, then you find the action, which integrated to the boundary now, reduces to an action on at the boundary. E to x, let me call it here, m over 4 pi of the time derivative of phi, and it's a space derivative of phi. Space means around the circle. Now, as Ganpathy explained, there is a problem when you have a boundary and you have a theory like this, you need to fix the gauge at the boundary. You need to supply with additional degrees of freedom, otherwise the theory is ill-defined. And you can see that because it's not gauge invariant. Okay? So what you do is you add a term that plays the role of gauge fixing if you want, or you add a term because you know that for physical reasons, I'm going to call it a gauge fixing term that will look like V A squared, A1 squared, but A1 is the X phi. And this is an arbitrary number here, which I will call a velocity for units. Just for units. So you can think of this as coming from fixing the gauge at the boundary, or that comes from adding degrees of freedom that cancel, in fact, this anomaly that this theory has at the boundary. It's an anomaly because if you carve essentially a region, then essentially the gauge transformations essentially are not fully respected at the boundary, so you need to. So this is Wen's argument that there is a cancellation, there's an anomaly inflow between the boundary and the bulk. Essentially just this. Okay? D2x is dx, D2x is called here dx. It's on the boundary only. Okay, S1 is a circle. I'm calling x this direction and t that direction. Okay. There is a non-Abelian version of this. I'll come to that later, but it's more elaborate. And that's the actual theory that Witten solved. This is sort of the baby theory. Okay. Okay. Let me discuss a little bit in a few minutes the observables of this theory at the edge. As Ganpathy explained, the observables in any gauge theory are so-called Wilson loops. Okay. But if I have a boundary, I can have a Wilson arc that ends at the boundary. Let me have a boundary, have a yellow. Here's the boundary. Here is the boundary. Here's the bulk. Okay, let me have a point A at the boundary, a point B at the boundary. And I'm going to draw an arc. Will be some curve that goes from A to B. Okay. In general, arcs are not allowed in the bulk because e to the I dx mu on some arc is not gauge invariant because the thing will change at the boundary. But since I fix the gauge at the boundary, I can do it. So in other words, what the gauge transformation at the boundary is a degree of freedom. Okay, so what is that? We call W gamma, it's called the Wilson arc, if you want, along this path gamma, is e to the I, the integral along gamma, dx mu by mu. Okay, but this is a gauge transformation as we saw. So this is e to the I along gamma that goes from A to B and is oriented dx mu d mu phi. Yes.
I think when you start writing.
Yes, I'm sorry about that. I don't, yes, this is the problem of writing. Okay, so this is just the circulation of this vector potential, is the exponential of that. But since this is a pure gauge, as I explained, because f is 0, this is the integral of a gradient. And integrals of the gradients we know how to do. It's just a difference of this quantity between the two endpoints. So this is going to be e to the I, let me call this phi of b, times e to the minus I phi of a. In the quantum theory, I have to be more careful. These are going to be operators. And so this exponential is a path order exponential, in fact. And so I cannot freely separate that. So this is like a time order product, similar to that. Okay. So this tells you that the natural observables at the edge have that form, are what the people call vertex operators. Okay. So they make their appearance. And not only that, so you could say, well, in general, you're going to have things like e to the I phi of x. This is allowed, okay? And so this is telling you this theory is actually invariant when phi is shifted by 2 pi in some integer, I don't know, k, r. Okay, because this is a circle. Okay, so phi essentially is periodic. Okay, it depends on p. So that means that phi is compactified. It's an arbitrary integer. Some integer is compactified. Yes, I'll do that. Yes. Okay. In addition to that, because this actually was a circle, we assume that phi of x plus L, where L is the perimeter of that, is equal to phi of x. But we're going to allow for changes because of that look like 2 pi times some integer times a quantity that is usually called the compactification radius. So you see this is like a winding number in the sense that you introduce. In this way I have done things, this radius happens to be 1. Okay, not in my units. Okay, but it tells me that the operators that are allowed have to look like this and they have to be 2 pi. Okay, let me tell you a few things about the propagator at the edge, and with that I will close. Talk about propagators. So now I need to use a time order product of phi of xt, say phi of 0, 0. You go to your, quantum theory, and you find with that Lagrangian, this is minus 1 over m, and some logarithm of x minus vt plus some I epsilon that I need because of the time ordering condition, divided by some microscopic scale, because it's a logarithm, the argument of a log has to be dimensionless, so I need to have some arbitrary scale. Typically, this is what we call the ultraviolet cutoff. Think of that being the magnetic length. Notice that depends on x minus vt only, so it's right moving. Okay, so this edge, the physics at the edge is chiral, much like what he found when he did the hydrodynamics of the edge from the quantum Hall effect. Okay. Now, what I want to do is to look for some operators. I'm going to look at what these operators tell me. I'm going to write an operator which is e to the I m pi and x, which is also functional. And I claim this is the electron operator. It has properties of a fermion, in fact. Let me call that psi e of x. We call this bosonization. As I say, always do bosonization. So the green function for this, or the propagator, as it should be called, is the time order product of what? Psi e dagger of x and t, psi e 0, 0, up to some normalization that I did not introduce. I have to give units to this thing. There will be something here that depends on the units. This, because the theory is actually Gaussian, this is actually E, the time order product of E to the minus m phi xt to the I m phi 0, 0. But because the theory is Gaussian, there is this marvelous identity that it exponentiates the time order product of this. Notice that phi itself is not an observable. The derivative of phi is because it will turn out to be like a current, but at the boundary. So this is upstairs. So if you use that definition, you find that this up to some units here, this is x minus vt plus I epsilon, to the power m. Let me call this quantity G electron of x and t. And notice that G electron of x and t and G electron of minus x minus t differ by a minus sign because m is an odd integer. So if m is an even integer, this will look like bosons. If m is odd, this looks like fermions. But it's not your garden variety fermion. It's not a pole. It's a multiple pole. It's already telling you that this theory, in general, is not associated with a free theory from the point of view of these fermions, because a pole is a multiple pole, except in the simple case of m equals 1, as we will see, that's the integer whole. Then you can do something which I will call the quasi-particle. And with this, I will end. Again, there will be some normalization, and it's just e to the I phi, the fundamental quasi-particle. If you do this for the quasi-particle, so you do the same computation, you find that this is the constant divided by x minus v. Again, plus I epsilon, this is that time ordering. But now there is a 1 over m. So it's a branch cut, it's singular. Okay? And that means that G for the quasi-particle at xt and G of the quasi-particle at minus x minus t differ by a phase, which happens to be e to the plus or minus I over m. And you notice that that's the same as the fractional statistics. So these vertex operators, essentially, the local observables, are the image of the bulk states, the bulk excitations, the electron, which is a fluid of electrons, so it has to be a fermion. And then you have these quasi-particles. Now, what I will not do today, because I am over time, I will start with that on Monday, is that in principle, it seems that I have an infinite number of possible quasi-particles, because I can raise this, put this factor, this integer p, whatever it is, to be anything I want. But notice that every m, you go back to the same observable. So in some sense, it's a natural truncation of the observables. So this theory that I constructed here is called the compactified boson. It's an example of a conformal field theory, of a chiral conformal field theory. But it's a special one that has a finite number of observables, which are distinct. So it will be the identity, so they normally will look like e to the I e phi, and p can be 0, which is the identity, 1, which is the fundamental quasi-particle, up to m minus 1. These are the distinct ones. The electron is not an actual quasi-particle, is essentially a derivative quasi-particle because it's part of the condensate. There is an important conclusion, and we'll come to that later, is that the only physical states, which are this, have to have the property that they don't braid with the electron. They are local with respect to the electron. And so you will see that, in fact, they have some simple locality properties because of that. Okay, so that's what truncates the spectrum. So this is in the technical literature, this type of conformal field theories are to be rational, because a finite number of so-called primary states, for us, will be a finite number of rational. For this reason, we call this a number of Anyon types. So it has m types of Anyons from 0 to m minus 1. Okay? So this is sort of the simplest example. And here we can do everything in front of you. When we come back on Monday, I'll show you some funny properties when you put this on a closed manifold. When we actually investigate the large gauge transformations, you're going to see an analog of this coming up in that case when you look at the quantization.
Right, time for questions.
Just to emphasize the point.
Yes.
The fact that e to the I phi
Yes.
is an Anyon and e to the I m phi is an electron,
Yes.
has to do, of course, with the commutations, definition of the commutations of the phi, which is, if I understand, hidden in this commutation of the AA that you wrote here.
Well, if
So
you
this,
want,
so this is the
so
hidden
this
point.
is essentially, where is it? It's
You
here.
did not write the phi.
It's here.
Okay.
Okay, this is telling you that the canonical momentum for phi is a space derivative of phi. Is this
Okay,
term.
this defines the commutation.
That defines the commutation relations for phi. But you see, this is inherited from the bulk, okay? So this is, it's a very simple theory in this sense, okay? You may think it's complicated, but it's a simple theory. You get a lot of the entire universal data is here, except for the so-called fractional spin that takes a little more work.
Yeah, sorry, could you please again explain why the CFTs have to be rational?
They are rational, it's rational in the sense that it's a finite number of so-called primaries.
Okay.
Which in here it means it's a finite number of Anyon types. Because
y-
this is cyclic, okay? Every M, they repeat themselves. They don't correspond to distinct excitations. Distinct fields.
Oh, okay.
Yes, yes.
Yeah, that's fine. Yeah, I didn't get why you only need to have a finite number of primaries. Could you explain that again very quickly?
Yes. It's the same story in the bulk with how many Wilson loops you can run.
Oh, okay.
It will
Yeah,
also
sorry.
it's the same restriction.
Okay, yeah, sorry, yeah, got it.
Yeah, so I have a question about this action that you wrote for the boundary.
Which one?
Is the value of V fixed there?
Sorry?
Yeah, what is the value of V there? Can it be arbitrary?
42. It's anything you want. Okay, this is actually where okay, notice that this part is topological. This part doesn't know about the metric for the same reason that the Chern-Simons action doesn't know about the metric. Once I break, and that's an important question, once I break, I fix the gauge. In fixing the gauge, not only I fix the gauge, I also break this huge additional symmetry, in particular, that makes a theory topological. Okay. After fixing the gauge, then you have various options. Because so now you could have things that have energy, in particular, but only at the boundary, because you are fixing the gauge at the boundary. And so you can think, so I wrote this term, which is like a square. So you think this will have units, okay? It's a velocity after all, okay? Now, microscopically, this could be essentially the drift velocity. You put an electric fields that trap my electrons and all of that. There will be an edge, as our chairman explained, and this is the drift velocity. But if you add the electron-electron interactions, this will change, will be shifted. If you are perverse and you write Coulomb, then it becomes somewhat singular, but it's all the same. But different. That's where the microscopic physics will enter, because those things have energy. Yeah. So this theory is not topological, but it's conformal invariant. This theory, this part is topological. And the topology only tells you the commutation relations, nothing else.
Yeah, so you said that you can put this on any metric you like.
Yes.
So if the
Smooth.
yeah, smooth, yeah.
Avoid black holes. Okay.
Yeah, I'm trying to. Okay, so what my question? Okay, my question was in that direction only. So if you have a singularity in your curvature on the surface, then what happens? Like if you put it on a cone. On a cone, for example.
The conical singularity is essentially akin to. It's not a black hole, but it's close to it.
I see.
You have to be careful. No, you don't want conical singularity.
But in principle, probably an experimentalist can try to put, he will see some. Yeah, I've seen people. Exactly. So I'm just trying to see from how I see.
For the same reason, we'll trap flux.
I see. Okay.
Conical singularity is essentially like an insertion of a quasi-particle in something.
Okay.
Yes.
Yeah, so I was trying to see from the thing which you wrote down, how do we see this? Is it?
I assumed here that all of these things were nice and smooth. I am a smooth kind of person.
Okay, thank you.
But no, point well taken.
A technical question, but should we be putting some normal ordering on these vertex?
Yes, you have the normal order. I can be fast and loose with that.
Also, like, so these.
Not only that, there are prefactors that I didn't write. And the normal ordering is about the prefactors. So for instance, in the case of the electron operator, this has to have units of 1 over the square root of a length by dimensional analysis, which I didn't write.
So you mentioned that these primaries correspond to certain quasi-particle types, right? So, I mean,
Yes.
so do the descendants correspond to something physical, or, I mean, what?
Yeah, they correspond to these quasi-holes, for example, that we discussed. So if you insert a quasi-hole at the boundary, then in the bulk, it turns out that you need to do this. You will not work with periodic boundary conditions. You actually have to twist the boundary conditions by an amount related to the charge, as we will see. And in that case, that condition will appear. So it will tell you how much charge is actually at the boundary.
Yeah, from the primaries, you can.
Oh, in the conform, they send.
L-1.
What about them?
I mean, do they correspond to something physical, like we can observe or something like that?
They correspond to, you get descendant fields when you take two fields and you bring them together. The same is true in the bulk. We are going to see that there are things called fusion rules. And the fusion rules essentially give you the leading terms, which are the non-singular. Yes, yes. And the fusion rules will be very important when we discuss non-Abelian statistics. So there are fusion rules at the boundary, and there are fusion rules in the bulk, and they are the same. So we're going to see that, in fact, there is a way to write the Laughlin wave function as correlators of things involving objects of this type, but in imaginary time. Okay, so the wave function has a CFT in some sense hiding in there by the choice of complex coordinates, essentially. And is related, so is the time, because the imaginary time version of this edge. It's the same theory.
So when you wrote down the commutation relations between between the gauge
1 and A2.
So you identified that from the Lagrangian pointing that you have P times Q dot.
Yeah.
All that is still classical, but when you promote them to operators, is the
Essentially, what
requirement?
they have is a Poisson bracket that they turn into a commutator.
But you need some state to define that, right? Like so then you
have
choose
some abstract Hilbert space on which they act.
Okay. So there is no constraint that you need to choose that the physical Hilbert space which you have written there.
No, actually, this is what is called the so-called Cartesian polarization, because I have to choose A1 to be the coordinate and A2 to be the canonical momentum.
Sure.
I could also take a so-called AZ, which is A1 plus I A2.
But when you promote them to operators, you mean you can just choose arbitrary Hilbert?
Yes, but once you do that, this is important, actually. Thanks for the question. In order to define the commutation relations, I need to choose a time surface. And then I need to choose what is called a polarization, which is I did without telling you. Okay? When I do that, I break this large symmetry that the classical system has. It's broken by that. Put it another way, and this is always true, if I define canonical commutation relations on some time surface, then in a sense I lose the large transformation. It's like in electrodynamics, to recover Lorentz invariance, you have to do some work, because when you use the canonical formalism, you don't see it.
Not all canonical transformations are allowed.
Yes, and so provided the changes of coordinates are smooth, they are the same. So here has a larger effect. Well, we can discuss this later. It has a larger effect that it violates this huge reparametrization symmetry that this theory has. Well, I'm going to run out of the door. Okay, so next time we're going to use this to rephrase what we know about the quantum Hall effect and then extend it, okay? And you're going to see that these results are going to be quite important in doing. Yes.
If you have a finite cylinder over there, not the cylinder going off to infinity, if you have a finite cylinder, this change in action will has terms corresponding to this.
Top and bottom.
So
in that case, that corresponds to what you call a process, an evolution. Imagine that you have some state and this some unitary evolution to some other state, and you call that a process. I'm doing quantum information. I have a unitary gate. Okay, so it takes the shift from some initial state, evolves into some final state, and you have to project on the final state. So that's what. So if I have actually, yes, I did here, if this is actually going for some finite amount of time, I need to specify the state here, and then I need to specify the so-called target state here, and this actually will be a matrix element, essentially, of a process.
Sorry, but the same thing that you, the whole formalism that you went on from there will not go through, right?
It will go through, except that we have to project in the final state what I have. I will have to project in whatever happens in the final state. I assume here that I am in the vacuum state, and go back to the vacuum state. If I have this to be finite, then I have to specify the initial and final states, right? It's like in any path integral.
I think he's referring to the fact that.
Yes, I know.
So that there be a breakdown of gauge invariant.
Right, but that means I have to specify the states. So this is the point. You need to specify the state here and specify the state there, and then you have to think of this as a transition matrix element. If you will. And all this is doing is telling you what this is like in any path integral. It's like this. It's not special to it. So you have some state, and some other state, and you evolve and you compute. Sometimes it's called a propagator. Many things are called propagators. That's one of the names for a propagator. It tells you how you go from some initial state to some final state and what the amplitude is. But you will need to specify that. Much I have to specify what the physics was here because of the lack of gauge invariance. I have to specify my initial and final